Today I will present the application of Ohmic heating in soup processing. Food processing is important because it ensures food safety, improves product quality and extends shelf life. One of the most common methods in thermal processing, which is destroy harmful microorganisms and inactive enzymes that cause food spoilage. However, conventional heating method has several advantages such as slow heating and even temperature distribution and the loss of nutrient and sensory quality. Soup is the food product that contains both liquid and solid ingredients such as vegetable, meat and seasoning. Therefore, proper heating is essential to ensure food safety, improve shelf life and maintain its flavor and texture. However, in conventional heating, the solid ingredient often heat more slowly than the liquid heating in even cooking. To overcome this problem, Ohmic heating has been introduced. It generates heat directly inside the food using electric current, resulting in faster and more uniform heating. Although this technology offers many benefits, challenges such as electrode founding and difference in electrical conductivity still need to be addressed. The principle of Ohmic heating is based on Joule's law, which states that electrical energy is converted into heat when the electric current passes through the conductive material. The equation is Q equals I square RT, where the Q is the heat generated, I is the electric current, R is electrical resistance, and T is heating time. It means that the amount of heat produced depends on the current, the resistance of the food, and the heating time. In a Ohmic heating system, food is placed between the two electrodes. When the alternating current passes through the food itself as electrical resistor generates heat internally. The process is called volumetric heating because heat is produced throughout the entire food rather than the surface. The heating performance depends on the factors such as electrical conductivity, voltage, food composition, and temperature. Since soup has a high moisture content and contain dissolved salt, it has good electrical conductivity. It means soup very suitable for Ohmic heating.
Next, I will explain the advantages and limitations of Ohmic heating in food processing, especially for soup products. First, Ohmic heating is highly efficient. About 90% of electrical energy is converted directly into heat inside the food. This makes the heating process faster and more uniform. Second, it helps preserve nutrients and vitamins. The food experiences minimal structural, nutritional, and sensory changes. Therefore, the quality of the final product is maintained. Third, heat is generated within the food itself. This reduces the risk of dirty, scorched, or burnt surfaces. As a result, maintenance costs can be lower. Finally, Ohmic heating is environmentally friendly. It can effectively process foods with large solid pieces and high solid concentrations. However, Ohmic heating also has some limitations. First, electrolysis and electrode corrosion may occur, especially at low frequencies. This can lead to metal contamination in food products. Second, the installation and operating costs are relatively high. Therefore, it may not be suitable for small-scale industries. Third, foods with high fat, oil, or very low water content are not suitable for Ohmic heating. This is because fats are poor conductors of electricity. Lastly, runaway heating may occur at high temperatures. This happens because electrical conductivity increases as temperature rises.
Let's see the sustainability contributions of Ohmic heating in soup processing. There is food, environmental, and economic sustainability. For food sustainability, Ohmic heating provides valuable food constituents that contributes to healthy longevity. Next, contributes to quality characteristics such as color, flavor, and texture to maintain sensory quality of food items. Sustainable in production of high-quality food, sustainable to preserve nutritional quality of food, inactive bacteria and enzyme also reducing fouling. Next, contributes to improve shelf life and reduce food waste. Then, Ohmic heating also contributes to a sustainable inhomogeneous heating, faster heating works and short heating time, less energy usage and improved product value and food safety. Also, Ohmic heating contributes to prevent overheating of surface of solid food and improve sensory quality. For environmental sustainability, Ohmic heating contributes to sustainable in cleaner and more environmental friendly process, produce no waste and no steam or not require water. Also improve energy efficiency and need lower energy in pasteurization application. Lastly, for economic sustainability, if it's sustainable by rapid time process, increase efficiency of food products, also produce high value products, can reduce cost and process time. Also, Ohmic heating sustainable in economical technologies for thermal process. Next, let's look at the challenges of ohmic heating in soup processing. Firstly, electrode falling and corrosion that occur because of electrochemical reactions and metal ion movement at food electrodes interface during heating process. Then occur uneven heating of solid and liquid, meaning that solid particle being heated slowly, then surround the liquid. This is because of differences in electrical conductivity between soup particles and liquid. Next, we have challenges about cold spot determination, where solid heated faster than liquid and result in cold spot in liquid. Maintaining homogeneity in viscous soups also a challenge in soup processing. Mass transfer during heating is limited to maintain the homogeneity in viscous soups. So industrial practice overheat the liquid to increase driving force for heat transfer, but it can lead to excessive liquid phase process and surface of suspended particle that lower the value of stabilized products. Lastly, challenges in soup processing that contain fats and oils causing from shortage of electrical conductivity. Next, we go to the industry issues. The issues is challenges of establishing industrial scale processes. Reaction of electrode falling and corrosion cause the process establishment more complicated. However, with good control and good plan of critical control and hazard analysis, it will be easy to monitor large scale of ohmic heating system. Then issue unlimited commercialization by food industry. Although ohmic heating provide better nutrient retention, high energy efficiency and others, however, it is not suitable for large scale commercial because of its high cost limits.
So next, I will talk about the application of ohmic heating on industry. The first is sterilization. It is used to destroy the harmful microorganisms such as bacteria, yeast, molds, and viruses to ensure the food safety and to extend the shelf life. It is used temperature above 100 degrees Celsius. For soup and broth product, UHT processing will heat the product at 135 degrees Celsius to 150 degrees Celsius for 2 to 5 seconds. The heating time and temperature must be carefully controlled to maintain the product quality. Next is pasteurization. It is commonly used for liquids product. It's to reduce the microbial load but does not destroy the spores, so the product required to be refrigerated storage. The two main methods are LCLT at 63 to 65 degrees Celsius for 30 minutes and HTST at 71.5 to 74 degrees Celsius only for 15 to 30 seconds. This process will help to preserve the food's nutritional and sensory quality.
Next, thawing and blanching. Ohmic heating provides rapid and uniform heating. It thaws frozen ingredients faster than water thawing while reducing the nutrient loss. During blanching, it also minimizes solid leaching and preserves more water-soluble nutrients. Lastly is continuous thermal sterilization. It is a process that continuously sterilizes food products and it provides gentle and rapid heating to ensure the consistency of product quality. And it is more energy and time efficient compared to other sterilization methods.
Let's move on to the recommendation and the improvement. First, for the soup chunks, our improvement is moving away from a traditional system where liquid and solids are mixed blindly, which causes uneven dangerous heating. To fix this, our recommendation is to perform targeted brine infusion, which means boil soggy vegetables or meat in salt water and use inline sensors to match the electrical conductivity of the bone and solid perfectly. Second, for the burn electrodes, our improvement focuses on stopping the severe burning and tearing or falling of starch and protein onto the machinery which ruin energy efficiency. Therefore, our recommendation is to upgrade the power supply to high frequency AC between 10 to 30 kHz and use titanium or MMO coated materials so particles cannot stick to the surface. Third, regarding large dense food, our improvement is overcoming the physical limit where standalone ohmic heating cannot warm up the very center of massive dense food chunks fast enough. Our recommendation is to adopt a two-stage hybrid configuration where a microwave preheats the center of large solid first, followed immediately by the ohmic column processing the liquid broth. Finally, for the carbon footprint, our improvement is transitioning the factory from relying on dirty fossil fuel electrical grids to a highly sustainable green processing cycle. Our recommendation is to hook up the ohmic processing line to renewable microgrid using solar or biomass and use counter-current heat exchangers to trap and reuse leftover heat. In conclusion, ohmic heating is an advanced engineering alternative that uses internal joule heating to overcome the limitations of conventional heat transfer. It helps preserve nutrients, color, and texture while achieving commercial sterility. In addition, it offers high energy efficiency, reduced processing time and water consumption, and recent technological improvements have solved issues such as electrode falling. Overall, ohmic heating is a promising technology for the future of sustainable and high-quality food processing.